All right. Let's see. I think we should be set up. Yeah, I do have me drinks. I do have me keyboard. Paul, hello, sir. How you doing this fine day, sir? I hope you had a good weekend. I threw off a binder just now, but I fixed it. There we go. Yeah, how you doing, sir? How's it going? Let me just, there we go. It's all nerd shit again. I just wanna, hang on. I gotta open this map, and then I gotta go cargo run. Check Tessie's Discord? Oh god. What happened this time? Don't want to write it all again. You got notes to come in for a job interview on Thursday. Oh, nice. Nice. That's amazing. Man, you can do it. I believe in you. Also, it's like 3 words. Alright, it's a bit more, but yeah. I don't know why Automod triggered on that. Unless you get fucked over. You won't, man. You can do it. It's gonna be fine. Let me just let me test if my program crashed since I made it. In the middle of a game, big man? Oh no. Fair enough. Oh nice, alright. It didn't crash when I asked follow age without being a follower. And it just worked for you. I still need to fix that date, but that's a minor concern. At least it gives something back. Nice. That's good shit. And use result that must be used. Oh yeah, it's complete. Whatever, whatever. I'm gonna be learning about some new stuff today. Or, well, relearning something that I kind of went over with a while ago. Oh god, my potion is horrible. And I do need some water. Thank you for that, Zaha. Oh, that was a big hydrate. Let's go. Let's see, I found this tutorial that should explain some stuff. But we're not gonna go into that. First of all, I thought it was like, hey, you need to look into this. Awake async is new. Do. Oh, here we go. The multi-threaded web project in chapter 1 is especially relevant. Update in February 25. The book adds a new chapter on async await that's even more relevant. Alright, let's have a look at that first. Fundamentals of async programming. I mean, I did work through this already. But at least I can go through it and see if it has something that I forgot in the meantime. Let's have a look. Many operations we ask the computer to do. Whoop. Now, I want to make the text a little bit bigger, but that might be a bit too much. Alright, zoom out a little bit, go up, zoom out one more. Yeah, that's fine. Many operations we ask the computer to take a while to finish. It would be nice if we could do something else while waiting for those long-running processes to complete. Modern computers offer 2 techniques. Yeah, you can parallel or concurrency. To improve parallel concurrent programs, we encounter new conditions inherent to async programming, where conditions may not finish sequentially in the order they were started. Alright, yeah, I did work through chapter 16 and the example they had there today already. This chapter builds on the use of threads for parallelism and concurrency by introducing an alternative approach to async programming. The future streams async await syntax that supports them and the tools for managing and coordinating between asynchronous operations. Let's consider an example. Say you're exporting a video you've created of a family celebration. An operation that could take anywhere from minutes to hours. The video export will use as much CPU and GPU power as it can. If you had only one CPU core and your operating system didn't pause that export until completed, you wouldn't do anything else on your computer while the test was running. Fortunately, your computer's operating system can and does invisibly interrupt the export enough to let you get some other work done simultaneously. Yeah, okay, this is more, hey, this is what async is for. I think we pretty much get the idea. You want to do multiple things at the same time. We could and we could avoid blocking our main thread by spawning a dedicated thread to download each file. However, the overhead of those threads would eventually become a problem. It would be preferable if they didn't block in the first place. You could also be better if you could write the code in the same direct style we use in blocking code. So we're doing that. That's exactly what Rust's async, short for asynchronous, abstraction gives us. In this chapter you'll learn all about async as we cover the following topics. How to use it, basically going to redo chapter 16, how multithreading and async provide complementary solutions that you can combine in many cases. Before we see how async works in practice though, we need to take a short detour and discuss the differences between parallelism and concurrency. We've treated parallelism and concurrency as mostly interchangeable so far. Now we need to distinguish between them more precisely because the differences will show up as we start working. Consider the different way a team could split work. On a software project, you could assign a single member multiple tasks, assign each member one task, or use a mix of the two. When an individual works on several different tasks before any of them is complete, this is concurrency. Maybe you have two different projects checked out on your computer, and when you get bored or stuck on one project, you switch to the other. If you're just one person, so you can make progress on both tasks at the same time, but you can multitask, make them progress. Yeah, so you switch up and down. This is concurrency because you're still you're doing them like in between, kind of at the same time, but they're not both getting worked on at the same time. When a team splits off a group of tasks by having each member take one task and work on it alone, this is parallelism. Each person on the team can make progress at the exact same time. Yeah, makes sense. Fair enough. Both these workflows, you might have to coordinate between different tasks. Maybe you thought the task you assigned to one person was totally independent from everyone else's work, but actually requires another person on the team to finish their task first. Some of the work could be done parallel, but some of it was serial. It could only happen in series, one task after the other. Yeah, so over here, after A2, in task A, this is standing still until B3 is done, and then we can go on with A3. Yeah. Likewise, you might realize that one of your own tasks depends on another of your tasks. Now concurrent work has become serial. Parallelism and concurrency can intersect with each other too. If you learn that a colleague is stuck until you finish one of your tasks, you'll be able to focus all your efforts on that task to unblock your colleague. You and your colleague are no longer able to work in parallel, and you're no longer able to work concurrent on your own tasks. Okay, yeah. So that's just basically an overview. Futures and the async syntax. I don't want to see like the whole index every time, but I don't think it can be helped easily. The key elements of async programming in Rust are futures and Rust async and await keywords. A future is a value that may or may not be ready now, but it will become ready at some point in the future. This is the same concept shows up in many languages. Yeah, I mean, I know promises from JavaScript. Kind of. I don't work with them a lot because nowadays we mainly use signals for that, depending on what kind of JavaScript you're working though. REST provides a future trait as a building block so that different async operations can be implemented with different data structures but with a common interface. In Rust, futures are types that implement a future trait. Each future holds its own information about the process that has been made and what ready means. You can apply the async keyword to blocks and functions to specify that they can be interrupted and resumed. With an async block or async functions, you can then use the await keyword to await a future. Let's wait for it to become ready. At any point where you can await a future within an async block of future is a potential spot for that async. Sorry, at any point where you await a future with an async block or function is a potential spot for that async block or function to pause and resume. The process of checking with the future to see if its value is available yet is called polling. Yeah. Some other languages also use async and await keyword for async. You're familiar with those languages, you may notice some significant differences in how Rust does things, including how it's handled the syntax. That's for a good reason, of course it is. It's always for a good reason. In writing async, we use async and await for most of the time, run compile step to equivalent code using the future trait, as much as it compiles for loops into equivalent code using the iterate trait. Because Rest provides the future trait though, you can also implement it for your own data types as needed. Many of the things we'll see throughout the chapter return types with their own implementation of future. We'll return to the definition of the trait at the end of the chapter and dig more into how it works. Yeah, okay. To keep the focus on this chapter on learning async rather than juggling parts of the ecosystem, we created triple TRPL, the Rust programming. It re-exports all the types, traits, and functions you need primarily for the futures and Tokyo's crates. The future crate is an official home for Rust experimentations for async code, and it's actually where the future trait was originally designed. Tokyo is most widely used async runtime in Rust today, especially for web apps. There are other great runtimes out there and they may be more suitable for your purposes. We use Tokyo Crate under the hood for TRPL because it's well tested and widely used. Okay, in some cases TRPL also renames or wraps the original API to keep you focused on details relevant to this chapter. If you want to understand it, no, I'm fine for now. Alright, let's see. Cargo, new, hello, async. We're gonna open that, cargo at TRPL. You can now use various pieces provided by TRPL to write out the first async program. We'll build a little command line tool that fetches two web pages, pulls the title elements from each, and prints out the title of whichever page finishes that whole process first. Okay. Okay, so we're in here. Let's get in Nvim going. Get this little terminal at the bottom. And we're gonna open our main file. There we go. Oh, we already have TRPL. I don't know why we do the extern create requires for MD book test. Sure, man. TRPL. Use TRPL, and we want to get the HTML from that. And then over here, I don't know why the main is giving us an error. Alright, it doesn't know either apparently. Alright, so it's an async function, page title, URL will be a borrowed string. We're going to return an optional string. So it's let response is TRPL. Alright, so we're just getting a URL. And we're gonna wait for the response of that. Then we get response text, text. That's response dot text. And we're gonna wait on the answer, and then it's HTML parse. I'm assuming we're just parsing through the HTML, and after that we're gonna define. It's gonna be like, hey, we want to get, yeah, first title. Okay. Excuse me. That's a response underscore text. We want to get the first title. We're gonna do a little mapping action. Title. Yeah, we want to get title element. That's gonna be title element.html. And we're gonna return that. Alright, so I'm assuming this just gets like, you get the URL, you get a text from that, and after that you parse it and you get the first title. And you return the HTML inside of that title. That makes sense. Yeah, and it's all async. Triple get function to get it. For the get function, we have to wait server. Yeah, we have to wait for a response, so we're using await. We have to explicitly await both these futures because futures in Rust are lazy. They don't do anything until you ask them to do with the await keyword. Yeah. This might remind you of the iterator thingy. That's fair. It does. Okay, note this is different behavior from when we saw the previous chapter using thread spawn, where the closure we pass to another thread starts running immediately. Yeah. Yeah, the moment you open new thread, it just starts running. It's also different from how many other languages approach async, but support for us to be able to provide its performance guarantees, just as with iterators. Yeah, okay, this is just explanation of the code, but the code's pretty clear in my opinion. Sorry, why is it? Note that Rust await keyword goes after the expression if you're awaiting, not before it. That's a postfix keyword. This may be different from what you're used to. Yeah, I think in JavaScript it's await. Yeah, you used the await before. But with promises, you give it an anonymous function. Or a lambda function is the official term, I guess. Oh, they got rid of like the response in this example. So you do get.await.text.await. I mean, I guess we could do that as well. We just paste this over here. We add a little dot to it. Get rid of this. Wait, what's up? What did I do wrong? Um, dot await. Oh, yeah, yeah. There we go. Yeah, so this is basically the same without like one declaration less, which I guess is good. With that, we successfully written our first async function. Before we add code to main, let's talk a little more about what we've written, what it means. Rust sees a block with the async keyword. It compiles it into a unique anonymous data type that implements the future trait. When Rust sees a function marked with async, wait, it sees a function marked with async, it compiles it into a non-async function whose body is an async. Oh, difference between a block and a function. Yeah, there we go. Sorry. Whose block is an async, whose body is an async block. Alright, so it gets a function and just puts a block in there with the async keyword. Fair enough. Async function return type is the type of the anonymous data type the compiler creates for that block. Thus, writing async fn is functions to write a function that returns a future of the return type. To the compiler, a function definition such as the async page size of list 7 is equivalent to a non-async function defined like this. Okay, so over here we just return a function. Okay, so you just make an async move in there. You do your async stuff. Ah, there we go. Yep, that makes sense. Uh, no, that's fine. We just want to get on with it. Determining a single page style. To start, we just get the title of a single page. Then we pass the URL page title and wait the results because we produce future by match. Yes. Wait, this is the one. Because the value produced by the future is an option string, we use a match expression to print different messages to account for whether the page had a title. Fair enough, you can not have a title. That's an option. Okay. Yeah, so over here we're gonna make the main async as well. Then wait, no, this is the example of the other one. This is also collecting args from yeah, unfortunately this code doesn't compile. The only place we use the await keyword in async or block, and rest does let us mark the special main function as async. The reason main can be marked async is that async code needs a runtime, a Rust script that manages the details of executing it. Main program can initialize runtime, but it's not the runtime itself. Okay. Most languages that support async bundle runtime, but Rust does not. Instead, there are many different async runtimes available, each of which will make trade-offs suitable to its use case it targets. For example, a high throughput web server with many CPU cores and large amount of RAM is very different needs than microcontroller with a single core, small amount of RAM, and no heap allocation abilities. The grades that provide us runtime also often supply async version of common functionality such as file and network I/O. Here, for the rest of the test, we'll use the run function from the TRPL crate, which creates a future as an argument and runs it to completion. We can see calling run setup as a runtime that can be used to run that's used to run the future it passed in. Once the future completes, our run returns whether value for the problem. Yeah. We could pass the future return by a page directly to run, and once it completed, we could match on the resulting option string as we tried to do in lesson 1.3. However, for most of the code chapter, most async codes in the real world will be doing more than just one async function call. So instead, we'll pass an async block that explicitly awaits the result of the page title call. Yeah, okay, so over here. Oh, wait. Okay, we still want to get apparently from the command line. Alright, we'll just do it. Let args, args, you're gonna be a flag string, and that's std env arguments stf, excuse me, std, dot collect. Alright, and after that it's gonna be trpl run async. And then we just get the URL. Oh, let URL. We're gonna borrow from URL. Oh, sorry, from args. From the args, we're gonna borrow the first argument. Then we match that. So you match the results from page title. Oh man, my typing is not good today. URL, we're gonna wait for the result. After that, if we have a title, it's gonna be print line title for URL was title. And if we get nothing back, we're just gonna print line URL has no title. Main function. Oh, sorry, I did still declare it as async, which is not allowed. It just explained it to me. Alright, so over here, if we go cargo, run HTTPS, oh sorry, minus. Let's just do google.com. www.google.com. Boop. It's gonna compile everything for the first time, so it's gonna take a little bit. Almost there. 189 out of 190. There we go. Title for Google was title Google title. I think we're inner HTML. Yeah, we're just getting full HTML of the title, but we need the inner HTML. Alright, so just to check, gonna run it again. There we go. Google. Alright, so run this code. We get the break we expect initially. But after code for a two-sides cancel, let's briefly turn our attention to how futures work. Each await point that every place we use the await keyword represents a place where control is handed back to the runtime. To make that work, first needs to keep track of the state invoked in the async block so that the runtime can kick off some other work and then come back when it's ready to try advancing it once again. This is an invisible state machine as if you'd written enum like this to save the current state for each await point. Page size of future, yeah, you get the initial, that's the URL, get await point, and text await point. Okay. Writing code to transition between each state by hand would be tedious and error prone, however, especially when you need to add more functionality and more states to the code later. Fortunately, the REST compiler creates and manages state machine data structures for async code automatically. The normal borrowing and ownership rules around data structure all still apply, and happily the compiler also handles checking those for us and provides useful error messages. Work through those later in the chapters. Ultimately, something has to execute the state machine, and that something is a runtime. Yeah. This is why you may come across reference to executors when looking into runtimes. An executor is part of runtime responsible for executing the async code. Now you can see why the compiler stopped us from making main itself an async function listing. Yeah, if main were an async function, something else would need to manage the state machine for whatever future main returned. Alright, so that's what Tokyo Thanks Tonight's doing for us in the Twitch application. Yeah, fair enough. But main starting point for the program is that we call the TRPL run function in main to set up a runtime and run the future returned by the async block until it was done. Note some runtimes provide macros, so you can write an async main function. Those macros write async fn main to be a normal fn main, which does the same thing as we did by hand in over here. Yeah, that's fair enough. Alright, we call page title with two different URLs passed in from the command line and raise them. Okay, so over here what we have one. Okay, so instead of URL, it's gonna be title future 1. And that's gonna be page underscore title for this one. I typed pare. Forgot me S. There we go. No, it's page, not parse. Page title. So we copy this one, paste it. I'm gonna go for number 2. And you're gonna be number 2. And then over here, how do we do this? Either left, right, right. That URL may be title? Oh yeah, the title may not be. Alright, so we're gonna get URL and maybe underscore title. That's gonna be a match. Over TRPL, we're gonna raise them against one another. title foot 1, title foot 2, and we're gonna wait for the response. This is gonna be match maybe title. You're gonna be like this. Yeah, we're gonna do this. Oh shit, add time. Whatever. We'll just keep on typing. Tippity typing. It's gonna be, oh, if only I could type either. Oh, did I forget a import? Yeah, we need both either and HTML. That's fine. So it's gonna be either and HTML. Save that. So it's either gonna be left. I don't know what these lefts are. I guess we'll find out. Or it's gonna be right. I don't know what these rights are either. Right, URL mobile mismatch type expected enum option. Oh, we need to return both the HTML. I think over here we're gonna hang on. Let's actually look. Yeah, because we have these print line, this return first. Match maybe tell space title is dead. A space title could not be. Yeah, okay. I'm fine with doing this because it just still tells us what happened. All right, event page title. So you're returning a tuplet, and one's gonna be a borrowed string, and the other one is gonna be the option of a string. Yeah. So this is gonna be let title, and then over here. No, excuse me, I need to close this one. And then we just return URL, comma, title. Option string is not the future, the trace future. Wait, what? Nani? Option string. Option string is a future, right? It's not a future, trace future. Return a string, an option string? Oh no, it's not. We've already waited it. So you either access or you don't at this point, but we don't have to wait for it to do. Okay, we begin by calling page title for each of the user supplied URLs. We save the returning fields as those. Yeah, we don't do anything with them yet. And they just exist as we can call this, but we haven't called them yet. Then pass the future to the race, which returns a value to indicate which of the futures passed to it first. And hood, race is built on a more general function select. Yeah, I've used select before. Select function can do a lot of things that the race function can't, but also in those. Okay, sure. Either future can legitimately win, so it doesn't make sense to return a result. Instead, the race returns as a type we haven't seen before. Either one. Either is somewhat similar to a result in that it has two cases. Unlike result, though, there is no noise of success or failure baked into either. Yeah, okay, so either the left hand fails or the right hand fails. Yeah, that's fair enough. Race condition returns left with the outputs. Yeah, okay, so it just returns the first one. Okay, so if we go over here and we go to Google and we run, what's the Rust site again? Oh, it's just up there. So we have this, and after that we say https://www.rust-lang.org. It's gonna build it, and then Google wins. I mean, I shouldn't be racing Google against anyone else. Like, Google's gonna win. We all know that. So if I just try to go for a glug.dev, I don't think I'm winning this one. Oh, I am. Why do I keep winning? That's never happened to me before. I never keep winning. Right, if we switch it around, did I make an error? HTTPS colon slash slash www.outlook.dev slash result unwrap request builder. Oh, I forgot a P in HTTPS. Alright, I can't win from Google, right? That'd be ridiculous, redonkulous. Google.com? I don't know why I'm winning from Google. I shouldn't be winning from Google. Okay. Hang on, I accidentally went to the top again. Yeah, where were we? We had that explanation. Is this the race already? Yeah, this is the race. Okay, so we're here. Yeah, explanation about race. That's just you have a small working web scraper picked up by a couple of URLs run to the command line tool that some sites are considerably faster than others. When in other cases, a faster size varies from run to run. More importantly, you've learned the basic of working with futures. Okay. Yeah, sorry, I was getting a little bit overwhelmed by the number of options there. That's fine. I plan to go for at least 2.5 more hours, so I should be able to get at least through this, and hopefully a part in the three-parter. We'll see. This section will apply async to some concurrency challenges we tackled with threads in chapter 16. Because we already talked a lot about we already talked about a lot of key idea here. In this section, we'll focus on what's the difference between threads and futures. In many cases, the APIs for working together, working with concurrency use async are very similar to those using threads. In other cases, they end up being quite different. Even when the APIs look similar between threads and async, they often have different behavior. And they nearly always have different performance characteristics. Yeah, create new task with spawn task. I remember that one. Wait, I didn't do. I did like do chapter 21. I think that's like previous chapter or something. I did the one with yeah, the final project. And I got through it. Like I actually understood what was going on, so I was feeling good about that. I just had to look up a few things, especially how trades worked. I haven't used those a lot yet, so that's I've used it once, I think. Uh, Alright, the first operation we tackled in creating a new thread with spawn was counting up two separate threads. Let's do the same using async. TRPL uses a spawn task function that looks very similar to the thread spawn API and the sleep function that is an async version of the thread sleep API. We can use these two together, implement the counting example down here. Okay. So I think we can get rid of most of this. There we go. Okay, I'm just gonna type this. Let's just see what happens. Run async trpl spawn underscore task. That's a new async block. And then we're gonna go for I in 1 through 10. We're just gonna print it, right? Print line. Beep boop. High number I from the first task. Alright, and then we put a little sleeper in here. Is it in the 4? Yeah, we sleep in the 4. Well, fair enough. That's a good place for a nap, I guess. So TRPL, triple sleep. We get a little duration from milliseconds, 500, so it's half a second. And we wait for that to happen. So every 5 seconds, this is gonna print a number from this task. Okay, and then we define a second one. It needs a semicolon, right? No, you don't, I think. I don't know, man. I don't know. Let's see. Sleep triple. Wait, this is for the, yeah, this is for the spawn task. We need to close the spawn task, obviously. Yeah. Wait, no, is it? Am I hallucinating? No. Oh, right, I see what's happening. So over here we go for I in 1 through 5. No, over here. We're gonna print, it's gonna high number I from the second task. And we sleep over here as well. TRPL, a little nap outside of the spawn. Duration will be 500 milliseconds from millis double L millis 500. And we wait for that to actually finish. Yo, Ace, how you doing? I'll be getting a little bit of a hydrate. Nice. Some good water. Alright, so in about 2.5 seconds, this will count up to 5. And in 5 seconds, this will count up to 10. And it should be happening kind of in between. Just gonna run it. We'll see what happens. We'll see how it does. Gotta go run Rhinos. There we go. Let's see. Yeah, that just... Wait, what? Hold on, the other one doesn't count to 10? 5 from the first task, but it doesn't actually continue? What? You are once again EP. Color me surprised. I hope you didn't have too much trouble with the bank, man. You noticed you had some troubles yesterday. I hope that's solved at least. But yeah, being EP, that's not gonna lie, that's just a classic, man. Starting points. The note from this point forward in chapter after example includes the exact same wrapping code with TRPL run in main, so we'll also skip it as we do with main. Don't forget to include it in your code. Fair enough. Yeah, this is what I meant. Like, where's my last 5 numbers? I miss a few. Like, it goes to 5 on the first task, and then it's like, nah, fam, we're not doing it. Including the fact that you may see mesh appear in a different order in your own terminal. Yeah, that's fine. Suppose stops as soon as the for loop of the body in the main async block finishes. Because the task spawned by spawn task is shut down when the main function ends. You miss beer? Why didn't you get some? Or can't you have it anymore? If you want to run all the tasks, if you want to run all the way to the task completion, you'll need to use a join handle to wait for the... You ran out and it's too late to get some? Oh wait, it probably is. Don't the liquor stores there like open at very specific times? That's probably hard liquor. You can get beer at a supermarket, I guess. Tragic disaster, yeah, man. I'd offer you some, but you'd have to come pick it up. So it might be faster to hit the shop. Because the task mode is shut down. Yeah, okay, sorry. You want to run all the way to the task completion. You will need to use the join handle and wait for your first task to complete. With threads, we use the join method to block until the thread was done running. In listing down below, we can use a way to do the same thing because the task handle itself is a future. Its output type is the result, so we also unwrap it after awaiting it. Okay, so we can save this in a variable. So we can say let handle equals this, and then down here, yeah, here, it's like handle dot await dot unwrap, because otherwise we'll complain that we're not unwrapping it. Alright, and now it should actually be counting to 10 on the second task. It switches around on this one. Where's it? Here. It starts with second, first, then first. After that first, second. Yeah, that's proper async stuff. So far it looks like async and threads give us the basic outcomes, just with different syntax, using await instead of calling join on the join handle and awaiting a sleep call. The bigger difference is that we didn't need to spawn another operating system thread to do this. In fact, we don't even need to spawn a task here, because the async blocks to compile to anonymous futures. We can put each loop in async block and have the runtime run them both to completion using DRPL join functions. Sections, waiting. Yeah, that's if you are running multiple threads. You have to wait for all of them to be done explicitly. But you also can't use the main thread while a side thread's run. No, that's wrong. You can use the main thread while a side thread's running. Shops only sell alcohol from 9 to 9. And you're just 10 minutes late. That's truly tragic, man. Okay, so hang on. I'm gonna try to predict this. Kind of. Because definitely gonna be. I'm just gonna go fit 1. We do not await fit 1, but instead use the new feature by triple join. We ignore the output even though it's tuple containing. Okay, that's fair. So we have that one. Then over here we should be spawning let fit 2. That's gonna be a TRPL spawn TRPL spawn underscore task. We want a new task. It's gonna be async. It's gonna be this block down here. We properly close that. Then over here, I'm gonna guess it's TRPL dash dash join. Yes. That's gonna be fit 1 and fit 2. And we're gonna await that one. Result tuple elements, not using it, we're not using arcs. Okay, we can get rid of the arcs thing. And we know we're not using, actually, let me let underscore equals. There we go. Only one warning because we're not using stuff. But it should now independently count, once it should count 5 the other to 10, and they should all be done before it stops. There we go. Well, it counts to 9 because we start at 0. Do we start at 0? Hold on. No! 1. Oh, we go between 1 and 10. Okay, that's on me. It's me being dum-dum. I just assumed we start at 0 because, you know, nerd shit. Okay, well, I'd say we pretty much got a grasp on this part. Try some of these variation rights views to see what they do. Nah. For an extra challenge, see if you can figure out what the output will be in each case before running the code. Nah, I'm fine, fam. I'm fine. Sharing data between futures will also be similar. We'll use the message passing again, but this time with the async version of the types and functions. We take a slightly different path than we did using message passing to transfer data between threads to illustrate some of the key differences between thread-based and future-based concurrency. Down there we'll begin with a simple async block, not spawning separate tasks as we spawn a separate thread. Okay. Oh yeah, we're gonna make I don't know what kind of it's TRPL channel. I don't know what kind of channel y'all spawn. That's fine. We're just gonna do it again. There we go. Another hydrate. Yes, sir. Gonna get some glorious water. Nice. Love me some glorious water. Alright, so we're gonna make a sender and a mutable receiver. That's gonna be TRPL, a channel. Creates an unbounded MPSC. That's multiple producer, single channel, single receiver. Okay. So we're gonna make a new file. Let file is new string. It's just gonna be hi. And then we're gonna send that text. Yeah, sender, send the value, and we're gonna unwrap. So we're gonna parse the result. Then let received equals rx.receive. We wait for a response, and after that we unwrap it. And we're just gonna assume this is fine, that there's no errors, which, you know, there probably won't be. Okay, so we're just gonna run this. I mean, it should be obvious, right? Yeah, we're sending it. It just hangs until something's like, all right, I can receive a message. And hang on, over here we're making it, then we're sending it. Then over here something's like, hey, I can receive a message, and we receive the message. That's easy enough. Yeah, this explanation is about channels because all the asynchronous and async in the triple run, everything within it can avoid blocking. However, the code outside this will block the function returning. Yeah, that's fair. That's just how it works. Uh, let's address the first part by sending a series of messages and sleeping in between them. Yeah, so every time we receive a message and then we sleep a little bit for false. But this is still gonna... Okay, let's just try it out. I just want to make sure I actually understand this correctly. Because I'm gonna use this a lot, I think. So I really, really just wanna skip it. Because I'm like, yeah, I know about how this works. But no, I want to get these basics down good. Actually, no. I am gonna be just like typing this over. That's too much, man. That's too much. There we go. Type annotation needed. Count in for type from parameter. You'll get your types. That's fine. Okay. Yeah. For every value in the vector, um, we're gonna go. We're gonna grab the sender. We're gonna send the value, and we're gonna unwrap the results. We're not using it, but that's fine. And then we're gonna sleep trpl sleep duration from millis. Yeah, it's 500 milliseconds, so half a second, and we're gonna wait for that to happen. I forgot the dot for that wait. There we go. And then we'll say, well, let some value is rx resv dot await. Oh, I can type? No, that's racy. That's not resv. You should be a v. You should also be an e. I was really off there. Damn. You're not a function, await. Stop thinking you're a one. And we're gonna print line resv, and that's a value. All right, is this still res rx dot? Oh, it's a function. Yeah. So we should actually go. All right, what I am thinking is gonna happen here. It won't, like over here. It's gonna send it, and then it's gonna wait for us to get it, and only after that is it gonna continue. So like this. Does that make sense? No, because it's still in the same thread. I don't know how this is gonna work. We could either be getting like waiting. Ah, yeah, okay. Yeah, because over here it goes. Yeah, we're sending this. Like it's gonna read the array for every element in the array. It's gonna send it. After that, it's gonna wait half a second. It's gonna send it again, wait half a second, send again, wait half a second, until it has all of them. After that, over here, we're like, hey, we're ready to receive. And it already has 4 messages in the queues, in the queue. So it's like, oh, hey, here, have something, and have something, and have something, and have something. So I'm just gonna make a little prediction over here. TRPL, TRPL. Shit. How did we run async? No, I want. What was it? TRPL. Run async. Future 1 is async that. Future 2 is async that. But I want to run a separate async function. Is this not TRPL run? Run async spawn task. That's the one. So spawn underscore task. Future. Yeah, that's gonna be an async block, basically. The async block's gonna have all of this without this one. Save it. Oh, do I need to move this? Mismatch the limiter, closing the limiter. Oh no, wait. I need to remove that one. Okay, redo. Okay, this was working, right? Yeah, this is working. Okay, let's actually read. We were over at this part. We use TRPL channel, sync receiver method, blocks. Oh, the receiver message is synchronous. Oh, that's really nice. Okay. So theoretically, hold on. If we go over here, I'm gonna undo. If I paste this in here, and if I cut this one out to go down there. Wait. Oh, I can't wait on that. Yeah. But can I just go this? This allowed? No. Okay. All right. Well, I might have gone a bit too far. All right. Let's have a look. I think I was still right. Let's see. This is the one that was working. Oh shit. All right. After starting up, I'll be back in a sec. Hmm. This is still a bit confusing to me, but I'm sure I'll figure it out in a little bit. And this is why I'm doing this. Like I just want to learn this. I want to get this. I want to know how this all works. There's a future. Yeah, there's the ad. Alright, yeah. I'll be back in a beat. Alright, and we're back. Alright, in this listing we use the for loopers all the time receiving sync channels versus doesn't yes have a way to write a for loop over an async series of items. However, so we need to use a loop we haven't seen before, the while-let conditional loop. This is the loop version of the if-let construction that we saw a while back. The loop will continue executing as long as the pattern specified matches the value. Uh, 1 second. Yes, sorry, had to take a little sippy of water. As many times as messages arrive, when the channel closes, regardless of whether any messages have arrived, the future will resolve to none to indicate there are no more values, and thus we see stop polling. That is, stop awaiting. Well, let loops puts all of this together. The result of calling that dot await is sum. Then we get the message and we can use the loop body, but just as we would with if let, if the result is none, the loop ends. Every time the loop completes, it hits the await point again, so the runtime pauses it again until some other message arrives. The code now successfully sends and receives all the messages. Unfortunately, there are still a couple of problems. For one thing, the messages do not arrive at half-second intervals, they arrive all at once. Yeah, because the whole everything is halted until this is done, and only after that are we like, yeah, we can receive stuff. Yeah, and we also need to close it with Control C. That's fair, because we don't send a none at the end. So presumably I should go none. Will this compile? No. Found enum variant none. Expected function found enum variant none. Okay. Let's start by examining why the messages come in all at once after the full delay rather than coming in with delays between each one. Within a given async block, the order to await keyword appears in the code, also the order in which they're executing when a program runs. There's only one async block listed there, so everything in it runs linearly. There's still no concurrency. All the txsend calls happen in spread with all of the sleep ones, and after that it receives. Yeah. To get the behavior we want, where the sleep delay happens between each message, we need to put tx and rx objections in their own async blocks. Yeah. Then the runtime can execute each of them separately using trpl join, just as the counting sample. Okay. I'm just gonna keep the code off screen. Once again, we await the result of calling that, not the future. Okay. So, what we need to do is we make let fit1 will be a cr no trpl spawn underscore task. It's gonna be an async block, and in there we're gonna do all of this. Save it. Async block may outlive its current function, but it borrows tx. Okay. So can I do like move tx over here? Oh wait, I need to use the hold on. Is it this? No, I'm just grasping at straws right now. Okay, how do I move that over? Let tx fit is let's sync. It just says async. Yo, Ox, how's it going? Just move? Right, but how? Like, I thought I was moving. Or do I need to move? No. No, that's not right. Wait, I just need to move the whole block? Ah. What? How does that work? Why does that work? Yeah, let's see. Over here, I should make a new future. Let's see. Let fit2 equals trpl spawn task async. We probably need to move it again. And then in here, we're getting all these lines, dumping them in there. Oh yeah, I forgot to do this. So now you should line out, and then we can trpl join. You need fit1 and fit2, and we need to await this one. Yeah, underscore equals. let underscore equals. Right? No warnings. Let's go. Another hydrate. Gotcha ace. I'm just gonna run this. Cargo run. I mean, the program won't stop now still because I haven't found a way to get a none. But at least they run concurrently. Nice. That was a good sip. Alright. So, you create, what do you have here? Yeah, they make one for, hoeveel do you have your programmer socks on? No, I got the most boring ass black socks on. Actually, me and my girlfriend, we bought like 50 pairs of the same socks and we just yeeted them all in one drawer and that's all the socks we have. It's a highly efficient system. I highly recommend it. Because matching socks is just the worst after you've done your washing. Yeah, alright. Well, oh, they just make this async blocks. They don't spawn a different task or a different. Yeah, no, they don't spawn a different task for it. What does the move do though? Rest async move. Async await, async move. Async closures, async. Let's see. Closures, design. Let me get a reader view on this. I love reader view. Fundamental spacing, I meant to solve is that normal closure can't return a value that borrows from the closure itself. This is a big problem in async because the execution of all async code is encapsulated in the future returned by functions. Right, but I want to know what the move actually does. It's very similar to what async f admits. CLDR, it moves all captures variables into a closure. It moves all captures variables into a closure. So it's basically saying all these variables that are in here are only for in here, or does it also move stuff from outside it inside it? Like in this case, we're using TX. So if over here I wanted to go tx.send none, for example, I don't think this is valid actually. It goes outside to inside. Yeah, so if I go over here, I go like, I want to add something to test. It should be like, oh, string from those borrow of move value, but yeah, okay, so it's complaining to me like, hey, we're borrowing or we're moving this into this closure, but using it outside it, you can't do it. Okay, nice. Thanks for the explanation. It makes it a lot clearer. It makes a lot of sense. And with a lot of digging, I maybe would have gone to the same answer. But yeah. Okay, so now it actually like prints one after the other, right? Does it also close? Hi from the future. Yeah, it also closes. Why does it close? Because we're not sending anything. Oh, because this has done sending. Like this closure has come to the end of the block. This closure, because the TX is removed, like it's removed from memory after we're not using it anymore, it's probably automatically sends like a non-value, and then the while let's like, okay, we don't have sum anymore, we can stop. Our export compile until the while let loop ends. The while let loop won't end until awaiting res3 produces none. Awaiting that will return none only once the other end of the channel is closed. Yeah, and the channel gets closed once it's removed from memory. Wait, over here they're going like it's not closed. But it does. Did Rust get updated since this got written, or is it because we're moving it out into its other space? Hang on, I wanna let's just make this normal async like they did in their tutorial. So we have that one. Oh, sorry, I actually need to close that. And then over here, we're gonna do this. We're gonna remove this one with, still need to close that, and we need to remove the move over there. Oh, and I forgot my semicolon because of course I did. I'm still not a Python programmer, but I just forget my semicolons, man. Alright, so now I suspect it won't be closing. Yeah, yeah, because this doesn't end the end of like its own task. So it doesn't actually get removed from memory, so it does send a none. Okay. Over here we change the box used to send message from async to async move. When we run this version of the code, it shuts down gracefully less message. Okay, I don't even need to be like the whole spawn task thingamajig. I could also just go like move. Over here we say move, and if we run this, hi from the future, close. Okay, wonderful. This AC channel is also a multiple producer channel, so we can call clone on TX if we want to send mesh from multiple futures. Yes. Yeah, hang on, let me actually look at the code. I don't think it will be very much surprising. So we have a TX, TX1, TX1 future. We're gonna move, let's see, you're using TX1 here, so TX1 gets moved into the closure. And then over here we make another TX future, and that's gonna send more messages in the same way. Okay, yeah, fair enough. Both async block needs to async move block so that both TX1 and TX2 get dropped when the block finishes. Otherwise, it will go back to the same infinite loop we started out in. Yeah, we go from triple one to triple join 3 to handle the additional future. Fair enough. And we see all messages from both sending futures, and because the sending future use slightly different delays after sending the, yeah, okay, we didn't run it, so actually didn't run like that. But yeah, that's just the same, but a bit different. Working with any number of futures. Okay, hopefully this will be more interesting. Although I'd say I already learned quite a bit. Let's. Why did I forget how to delete everything inside the closure? Vim remove inside closure. Moving to end and deleting inside brackets. CI. Oh, it's I need to. Do I need to use that one? Hang on. Let me go to line 6. There we go. Delete inside this. No. What? Is it B for block? Delete inside. Hang on. Delete inside block. It is B for block. There we go. Alright, actually, we'll just. No, I didn't need to save that because then it was gonna format it. Hang on. Working with when we switched from using 2 to 3 in the previous section, we also had to switch from using join to using join 3. Hang on, is my chat crashing? What's going on? No, it's fine. Just had to reconnect for some reason. Sure, Twitch, whatever makes you happy. It would be annoying to have to call different functions every time we change the number of futures. I agree. Happily, we have a macro from macro form of join in which we can pass an arbitrary number of arguments. It also handles awaiting the future itself, thus we could rewrite the code listing from there to use join instead of join. Yeah, okay, so, well, that speaks for itself. Like you just do the same, you do join exclamation as a macro and it just handles it. It's gonna be fine. This is definitely improvement over swapping to join 3, join 4 and so on. However, this macro form only works when we know the number of futures ahead of time. In real world though, pushing futures into a collection and then waiting on some of all of the futures to complete them is a common pattern. Yeah, that's the pattern we're going to be using. To check all the futures in some collection, we'll need to iterate over and join all of them, for which we have to join all. As long as there's an iterator, it will just go over it. So putting our futures into a vector and replacing join with that. Yeah. Yeah, so you just run them into a vec. Hold on, where's the vec? Show me the vec. Alright, so we collect futures. We have all these damn futures. And over here we join them into one vector and then we just pass them along. Fair enough. Oh, damn it! I was like, this makes so much sense. But no, it doesn't work. Okay, what's going on? This might be surprising. After all, none of the async blocks return anything. So each one produces a future output. Is that? Remember that future is a trait though, and that the compiler requires a unique enumerator for each async block. You can't put two different handwritten structs into a vec and the same result applied to the different enums generated by the compiler. To make this work, we need to use a traits object. Oh no, my mortal enemy, traits. Okay, hang on. I'm gonna work with this. So I'm just gonna copy all of this over. Whee! There we go. Copy, paste, save it, format it. Mismatch block, expected async block, found async block. Not to async block, even if identical have the same, consider appending your async block and casting them to a trait object. Yeah. Alright, so over here, most of it will probably be the same. Yeah, this is just all the same. Then over here, we create a vector of new boxes. And that's basically all. Alright, so we should go box new. Over here it's gonna be box new. And over here we're gonna use box new. Save it. Errors. Arguments to these functions are incorrect. Wait, what? tx1 foot, rx foot. Unfortunately, the code still doesn't compile. Oh god, I love this. Is amazing. It's like, here's a solution, but it doesn't work every damn time. I love the crap though. In fact, we get the same basic error we got before the second and third box new calls, as well as a new error referring to an unpinned trait. We'll come back to unpinned errors in a moment. First, let's fix the type errors on the box new calls by explicitly annotating the file of futures variables. What? You fucking what, mate? Let futures is vec box din future output. We need to. Okay, it wants to know what kind of boxes we're gonna pass it, which makes sense. Like it wants to know what it's dealing with. That's the whole point of Rust, wanting to know what you're dealing with. So we have a dynamic future, which will have an output, and that's gonna be this. Hmm. Oh yeah, unpin errors. They were going on about that, but that's fine. I hope. Um, yeah, so yeah, we get futures, then we annotate the trade with dynamic to market system within to market as dynamic. The entire trade reference is wrapped in a box. Finally, we state explicitly that futures is a fact containing these items. That's already made a big difference. Now when we run the compiler, we only get errors mentioning unpin. Although they are free of them, their content, yeah, the contents are basically the same. That's a lot to digest, so let's pull it apart. The first part of the message tells us that the first async block does not implement the unpin trait and suggests using pin or box pin to resolve it. Yes. Din future cannot be unpinned. Consider using the pin macro. Consider using box pin if you need to access the pinned value outside of the current scope. Okay. Finally, we use box pin to pin the futures themselves. Hang on. Later in chapters we'll dig into a few more details about pin and unpin. For the moment though, we can just follow the compiler's advice to get unstuck. In the listing, we start importing pin from std pin. Next, we update the type annotation for futures with a pin wrapping each box. Finally, we use pin to future themselves. Okay, let's just start with the easy part. We're gonna use std pin, right? Yeah, std pin. So we're gonna go pin colon colon pin, and we still want time duration because we're using that. And I want a little enter because that's just how I am. Then we need to do more to the box, right? Vec, pin, box, din. My lord, this is not readable. Oh my god. Okay, hang on. So this is gonna be a pin inside of a box. Sorry, an output inside of a future, inside of a box, inside of a pin, inside of a vec. Okay, and now we get mismatched types because we didn't actually make these into pins. Pin, pin, pin. Okay. So that should be able to do something. Hide more from messages the for future you. Beautiful. Beautifully gambled. There's a bit more to explore here. For one thing, using pin box T adds small amount of overhead from putting this future in one heap in the box. We're only doing that to get the types to line up. We don't actually need the heap allocation. After all, these futures are local to this particular function. As noted before, pin itself is a rapid type, so we can get the benefit of having the single type in the vec. The original reason we reached for box without doing heap allocation, we can use pin directly in each future using the std pin macro. However, we must still be explicit about the type of the pinned reference, otherwise Rust will still not know how to interpret these as dynamic trade objects. Makes sense? Which would we need them to be in the vec? Yeah, that's right. Before we add pin to our list of imports from std pin, we therefore add pin to a list of imports from std pin, then we can pin each future when we define it and define futures as a vec containing pins, mutable references to dynamic future type as listing that. What a word. What a word. Wait, we need them to be muted. Hold on. Okay. And then we can go. Oh, wait, hold on. Let me look up above. Alright, so instead of just doing this, we can wrap. Ah, yeah, I get it. I get it. We're just wrapping this all in a pin. Exclamation. We need a macro. I think. No, it's after this one. Yeah, there we go. Just like that. Can't find macro pin. Alright, we'll add it in a second. Just hold on. Just hold on. You're gonna be pinned. Pin. Pin. And over here, one more. Pin. I keep adding the T, man. I don't know why. Oh shit, it's add time as well. Lovely. And then unused imports. Yes. What's the pin macro? It's just okay. It's uppercase pin and lowercase pin. Pin. So we have pin and pin. Save it. Alright, and now it's going to complain over here that we do a pin and a pin. So we go to this. Save it. Ah, mismatch types. Expected struct, found struct, pin, mutable, async, block. Oh, it's getting async blocks now, and it's still expecting some kind of dynamic future. What did we do wrong? Async move. Did we do something wrong? To avoid unnecessary heap allocations. Got join all futures.await. Yeah, but we're still mismatch type. I mean, it seems to be only complaining about the first one, so maybe there's just I made a little mistake there. Like that'd be extremely reasonable. Found the found async block. What do you have at the first one then? It's still over here. Yo, Sidhu. Let's see. There, the ads are over. Yo, Sidhu, how you doing, man? How's it going? How am I doing? I'm pretty well. I just started my last week of work for well the, the next 2 weeks. I got this week to go, and next week gonna be off all week. And the week after that, I have to work 2 days, and then I'm off again. So it's gonna be great. Gonna be really enjoying that. You're good as well. Hey, happy to hear that. You had a good weekend as well. You noticed that you were doing a lot of work. Nice, yeah. Yeah, I'm looking forward to it, man. It's gonna be my first holiday since March, something like that. I got a few days off here and there. But yeah, I'm saving them up for later in the year. Gonna take the free time in the autumn and winter. I do heavily prefer those seasons. I'm just gonna throw everything I have in here away. Yeah, in here, delete inside block. And I'm gonna copy this over. Whee! Begin playing Enlisted again. What got you back in, man? Don't tell me it's the event. Men sweats? Yeah, you know it. There's always sweats in Enlisted. Especially once you get to the higher BRs. Like a lot of people prefer playing the lower BRs just to dodge the sweats. Which is valid, honestly. I still don't know what I did wrong. But I'm fine with that for now. I was just typing up a code anyway. We got this far by ignoring the fact that we might have different output types. For example, over here, the anonymous function for A implements future output is U32. The anonymous function for B implements output is string. And a third one, the, you sweat back. You wish you had time off. I mean, don't you get... I don't even know. Are you in school, Ace, or are you just working? Like in either case, you should get time off, right? You sweat back, Sidu. That's a proper answer, though. Alright, so if we make an async function, that's like 1u32, so that's just returning 32. You're full-time unemployed, you don't get to complain, man. Mr. Full-time unemployed wants some more time to be unemployed? Wait, that's a 1, not a y. I. E. Let us see equals async. True. Alright, yeah, and now we're gonna go like, hey, all of these are gonna do something. And it's not gonna be happy about that, I can tell you that much. Because all different types, it's all different typings. Why do you compile? How do you compile? Do you compile? One hello and through. I mean, I guess you can all display them. Huh. Honestly, I didn't expect that to run. I was expecting an error there. What the heck? We can use join to await them because it allows us to pass multiple future types. Oh, join just other people don't deal with this for us. We cannot use join all because that requires all the futures passed to have the same type. Remember that error is what got us started on this adventure with Ben. Fair enough. Okay, that's pretty cool though. I like the future. This fundamental straight up. You have school kinda. That doesn't sound very convincing. Also, you get off for that, so you know. Even if there's this same scenario with face with working, that even those futures are not special, even though we have some nice syntax for working with them, and that's a good thing. When we join futures with join family of functions and macros, we require all of them to finish before we move on. Sometimes, though, we only need some futures for a set to finish before we move on. Kind of similar to raising one future against one another. Yeah, if you want to just get the first response from a few things, then you know don't need to wait for all of them to finish. Uh, Over there we use triple race to run two futures slow and fast against one another. Yeah, so there's probably going to be one. Yeah, it's one that's waiting 100 milliseconds, and there's another one that's waiting 50 milliseconds. So this will just print like slow, no fast. It's gonna print fast every damn time. Each future prints a message when it starts running, pauses for some amount of time, and by calling and awaiting sleep, and then prints another message when it's finishing. Then we pass both slow and fast to the race condition, wait for one of them to finish. The outcome is to surprising fast wins. Unlike when we raced back to our first async functions, we just ignore the either instance and return them here because all of the interesting behavior happens in the body of the async block. Notice that if you flip the order of arguments to race, the order of the startup message changes even though the fast future always completes first. That's because the implementation of this particular race function is not fair. It always runs the futures passed in as arguments in the order. Yeah, so it's always run like the first you pass and then the second. So the first always starts running first. So it gets a head start in the race. That's not a fair race though. I mean, I have to do some stupid stuff to get papers for my school, so I can be real unemployed. Yeah, that should go for now. I mean, I know you have some trouble, some health trouble, so that's fair enough. Even though fast food is completed first, that's because the implementation of this particular race is not. Yeah, sorry, I was reading that. Recover from first async that at each await point, Rust gives us a runtime a chance to pause the task and switch to another one if the future being awaited isn't ready. The inverse is also true. Rust only pauses an async block and hands control back to a runtime at an await point. Everything between await point is synchronous. That means if you get a bunch of work in on an async block without an await point, that future will block any other futures from making progress. You may sometimes hear this being referred to as one future starving other futures. Yeah. Yeah, if there's not a hint of point where we check on all the other things that could be running, it's not going to hand that thing off. That makes sense. In some cases, that may not be a big deal. However, if you're doing some kind of expensive setup or long-running work, if you have a future that will keep doing some particular task indefinitely, you'll need to think about when and where to hand control back to the runtime. By the same token, but school requires a full attendance, which is currently not possible. Oh shit, man. That sucks. Is there like is there not some kind of permit you can get for that? Because usually there are ways, especially if you have a particular diagnosed trouble, to get some help or to get it sorted out. But how could you hand back to the runtime in those cases? Let's simulate a long-running operation. Okay, so we're gonna make a slow function that's just gonna wait for an amount of time that we determine. Okay, fair enough. So we're gonna make that. Oh, not over there. We're gonna make it over here. So make function slow. It's gonna have a name, string, and milliseconds, which is gonna be an unsigned 64-bit integer. We're gonna say, hey, you're gonna thread sleep. You're gonna sleep for a duration from milliseconds. Oh, that is another height rate. One moment. I'm just gonna go print line. This one name ran for MSMA. Save. Actually, we're gonna do that. Filter resolve. Use of an. Oh. Yeah, there we go. Hydrate. Yes, sir. There we go. Got another hydrate. We forgot the import probably. Oh yeah, we forgot thread. We don't need the pins anymore. That's gone. Alright, and we can remove all of these. Oh, that's too much. These. Yeah, there we go. Okay. Code uses sleep instead of triple sleep, so we can call slow will block the current thread for some number of milliseconds. We can use slow to stand in for real world operation. Yeah, fair enough. Over there we use slow to emulate doing this kind of CPU bound work in a pair of futures. Alright, so we're gonna make an async function that's gonna do like 3 slow thingies. Alright, so do let A is async. We go print line A started. And then we're just gonna go slow with A. Yeah, we'll just add some milliseconds. Slow. I added an end to it. I didn't mean to. There. Now it's just slow. Expect a semicolon. You can have your goddamn semicolon, man. Wait, what? Let A. No, you have your semicolon. There we go. I was about to say. So we copy this, we paste it a few times. We're making it a few different times. Then we're gonna TRPL should be over here. TRPL sleep for a duration 1/20th of a second, I guess. Sure, man. From millis 50, and we're gonna wait for that to happen, and then we say println. There we go. Print line A finished. Oh, did I forget some things? Yes, I did forget some things. Okay, then we basically have an identical B function that I don't want to type out. So we're gonna just copy that. Save it. Hang on, save it. Thank you. Oh, there's mosquitoes entering. I need to close my window. Window's closed, but now I got two mosquitoes in my room. I don't want mosquitoes in here, but it's too late now. I didn't know it was during dark already. TRPL, we're gonna erase number A and B. We're gonna wait for the results. Okay, yeah, we still have that. Okay, let's just run it to see what happened first. So what are you doing? Alright, you're running all of A and then all of B. Because there's nothing in between that hands it over. And like it explained, race always goes left to right. So first you're gonna execute A, that's gonna start. And there's no handoff point at any point here. So I have a suggestion. I'm just gonna try this out. Because what in the middle of A, like after each one, I just let it wait for a little bit. Then it has a wait. And if my understanding do be correct, which it very well might not be, the awaits are like a handoff point where it can also hand it over to something else. So let's see what happens. Yeah, right. So now it can hand it over. Okay. I see what's happening here. So if it's waiting on something, it can start something else in the meantime. And it just needs to... Oh, shit. It just needs to... Oh, God. Did I remove too much? I probably did. Yeah, there we go. I fixed it. Okay, as with our earlier example, race still finishes as soon as it's done. There's no interleaving between two futures. Yeah, that's what we just went on about. Can already see kind of happening in list. Alright, yeah, over here it's... Yeah, because we have the sleep await right now, this one shouldn't be there. Because over here it can hand it over. So in this example it did. First it started A. And it went over here. It's like, oh, I have an await. We can start B. And it goes over here. And only after that it goes A finished. I got one less mosquito in my room. Let's go. Okay, we're still finished as soon as A is done. There's no interlinking between the fields. Yeah, okay, sorry, we went on about it. And this is just what we did. This is what we did. And now it can hand over because we have those awaits in between. The A future still runs a bit of handling control to B because it calls slow before ever calling TRPL sleep. Yeah, after that it can... Alright. We need to handback control to the current runtime. We can do that directly using yield now function. Oh. Okay, so over here we can go trpl yield now dot await await await. There we go. So we can place those in between. And we can place them in between all of these. Oh shit, I closed my terminal. Whoopsie daisies. Alright, so if we go cargo run. Damn it, missed fly. Missed the mosquito again. Yeah, now it can just hand it over left, right, however the heck it wants. Okay, well, that's a really useful one. This code is both clear about the actual intent and can be significantly faster than using sleep, because now timers such as the one used by sleep often have limits how granular they can be. The version of sleep that we are using, for example, will always sleep for at least a millisecond, even if we pass a duration of 1 nanosecond. Again, modern computers are fast, they can do a lot of 1 millisecond. You can see it for yourself by setting up a little benchmark. Uh, yeah, I mean, I believe they're right on this one. I don't need to benchmark it. That's fine. This means the async can be useful for compute-bound tasks, depending on what your program is doing. Real-world code, you won't usually be alternating function calls with the waypoints on every single line, of course, while yielding control in this way is really expensive, it's not free. Many cases trying to break up a compute-bound task might make it significantly slower, so it's better overall performance to let an operation block briefly. Always measure to see what your code's actual performance bottleneck are. The underlying dynamic is important to keep in mind though. If you are seeing work happening in serial, if you are seeing a lot of work happening in serial, yeah, okay. So if you see things happening after one another and you really expect it to be at the same time, check it out. Which makes sense. Hang on. Yeah, over here. Sorry. Make this terminal smaller again. There we go. That's how I want it. Oh, I can't. I can't save the terminal. Of course I can't. Okay, building our own async exception. We can also compose futures together to create new patterns. For example, we can build a timeout function with async building blocks that we already have. When we're done, the result will be building another block that we could use to create still more async exceptions. Alright, so this is like a theoretical thing how it works. So you make a slow async function that just waits for 100 milliseconds and then return I finished. Match timeout, slow duration 10 milliseconds await. Okay, message succeeds with message. If there's an error, it failed. Okay, let's implement this. To begin, let's think about the API for timeout. It needs to be an async function itself, so we can await it. Makes sense. First parameter should be a future to run. We can make it generic to allow it to work with any future. Its second parameter will be the maximum time to wait. If we use the duration, that will make it easy to pass along to TRPL sleep. It should return a result. If a future completes successfully, the result will be okay with the value produced by the future. If the timeout elapses first, the result will be an error with the duration that the timeout waited for. Nani? Sleep duration. Hang on. So we make an async that waits 5 seconds. Then we say slow. Okay, so we give the maximum time that it can complete in. And this will, well, this will wait 5 seconds. If it's not done in 10 milliseconds, we're like, hey, screw you, buddy, you're out there. Okay, well, let's have a little look. So it should be async function timeout. Alright, and you'll be passed just any future. We don't care about what it is, it's just gonna be a future. So you'll be future to try, true, try, and we have a max time. There's gonna be a duration. We're gonna return a result. That's either gonna be the output of the future. That makes sense. Or the duration. Oh yeah, the time that it took to time out. Okay. That returns. Wait, it's already... Okay. I don't wanna type all of this, so we're just gonna be pasting it. As that over here, we're gonna remove these lines. Save it. Uh, whoa. Okay. I forgot this one. And I forgot this one. There we go. Okay. So you're not returning anything, so it's fair that you're giving me some errors. Okay, that satisfies the goals for time. Now let's think about behavior. We want to raise the future past in against the behavior. You can use sleep to make a timer future from the duration. And use the raise to run the timer with what the future passed in. We also know that the race is not fair. Polling arguments in the order in which they are passed. Thus, we pass the future to try to race first, so it gets the chance to complete even if time max is very short duration. That's fair enough. Yeah, it's still like in a real life scenario, you would want this to be fair, like obviously. But for now, this should work. All right. So hold on. We're gonna. There we go. Um. So first of all, we're gonna make the timer. It's gonna be duration from. Oh no, wait, we already have that. Wait, what? We can use future sleep to make a timer future from the duration. Oh, that's yeah. So the sleep is gonna be TRPL sleep for max underscore time. Save it. Are you giving me errors? And then we have the future to try. The race will turn right. If future to try. Yeah, okay. So we should be TRPL race. We should be matching this honestly. So we go match TRPL race, sleep and future to try. We have the left arm. I'm kind of annoyed that it's doing the thingy, doing the thing, doing the red ribbons. There we go. There we go. Okay. I'm not looking at the code over there. I was just annoyed, so I want to look at it, but I won't look at it yet. Not until I don't get it anymore. Honestly. Oh, yeah, alright. They were just talking about, hey, we should let the future go first. So over here, future first, then we do time. Sleep. We call it sleep. So it's gonna be either left. I'm just gonna print line for now. Left. Or it's gonna be, no, wait, hold on. I want to look at this. How do you, yeah, you didn't match. You await it because obviously you have to await a race. Stupid me. So we go await. Then we go back. It's gonna be, oh, it's either colon colon. Yeah, that's fair. Output. And then we return okay on output. That's the F output. Yes. And then we have either right with some value we honestly don't care about, and that's gonna be R with max time. This can be gone. We can return this. Wait, you have an unmatched something? What art thou going on about? Let's see, what's not matched here? This telemeter might not be properly closed. No, we have one too many. Absolutely right. Oh. Oh no. Uh, oh, we don't have, we're not using, use TR triple, use triple either. Save it. There we go. Expected value found struct. Oh yeah, we don't need to add struct, we just do output over here. Alright. That can be gone. Yeah, we can remove this. Oh, that was a bit too much. Oh, duration is in there. Okay, there we go. Okay, there we go. So let's see, this should error. Honestly, this should just straight up give an error. Failed after 0 seconds. Okay, and then if we go, if we make the timeout instead of from millis, if we go like, hey, we give you 10 seconds. Just gonna wait 5 seconds and then we should get our little response. Yeah, there we go. Finally finished. In practice, you also work directly with async await and secondary with functions and macros such as join all, raise, and so on. You need to reach a pin now and again or use views from those APIs. Okay. October 24th, okay. Okay, we're gonna work with this. Alright. So with that, I don't want to do this tutorial anymore. So I found this little three-parter series. Let's get rid of all of this that we're not using. Thank you. We just have a main. It's beautiful. Yeah, someone called Jacko.io made a little introduction to like a three-part series. I want to get to at least like the first part tonight, and maybe we'll see how long that takes. Async await or async IO is a new-ish Rust edition. New-ish Rust added async. Oh, it missed break line here. Oopsie. Is a new-ish. Rust added async await in 2019 for comparison. C# added 2012. Yada 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 yada. Language feature. Oh, here it continues. It just put this sentence in here. It's a new-ish language feature that lets our programs do more than one thing at a time. It serves an alternative to meta-threading, though Rust programs often use both. Async is popular with websites and network services that handle many connections at once. Many here conventionally means 10,000 or more. This is sometimes called a C10. I mean, I'm definitely over engineering what I'm using this for because I doubt I'll ever get more than like five requests at the same time. I just want to do it like this. I want to cry about this. I want to cry in the future. Like, why the heck did I ever think async was a good idea? This series is an introduction to futures, tasks, and async I/O in Rust. Our goal will be to get a good look at the machinery so that async code doesn't feel like magic. We'll start by translating, desaturating async examples into ordinary Rust and gradually we built our own async runtime. For now, a runtime is a library or framework that we use to write async programs. Building our own futures tasks and I/O will gradually Make it clear what a runtime does for us. I assume you've written some Rust before, a little bit, yeah. I mean, some is really doing some weight for me here. And that you've read the Rust programming language, the book, or similar. Yeah, I've read that. The multi-thread server project, yeah, I did those. It takes a high level view including HTTP and streams, for example, while the series takes a lower level view. I heartily recommend reading the new chapter, but that's not a prerequisite. Alright, I honestly kind of skipped over the whole thread thing. The streams thing. Let's get started by doing more than one thing at a time with threads. This will go well at first, but we'll run into some troubles as the number of threads grows. Then we'll get the same thing working with async away to see what all the fuss is about. They'll give some example code to play with, and in part 1 we'll start digging into it. Okay, maybe for today we just do the first PC, the first bitsy. We'll see. We'll see how it do be going. If alright, so we just have like simplest full function. I'm just gonna paste it in because I want to play around with it. Yeah, I know I need thread. Hold on, std thread. There we go. We get thread. We also get duration. Sorry, where's duration from again? I thought it was just an std. std time, okay. So we go time duration. Save it. Alright, you're dead code, but that's fine. So over here in main, we just go full 5. Beautiful. So we run it and it says start 5, end 5. Done. And that took 1 second. Alright, so these threads are waiting 1 second. I want to make several calls to full at the same time. We can spawn a thread for each one. Click on play. Yeah, okay. So over here, we're making a mutable, let mutable thread. I see mosquito. Mosquito. It's on my screen. I don't want to hit my screen. And it flew off. God. I saw it and I missed it. Alright, let mutable thread handles. Which will be just your default fag. We don't need more than a default fag. It's fine. Alright, for n. Alright, so we go up to 10. We actually go to 10. We don't stop at 9 this time. We just add them to the little fag we have. So we go threads. Thread underscore handles dot push. Not pop, push. The other one. Thank you. Yeah, push, and it's gonna be thread spawn, and we move the value there, and it's gonna be full n. So we're just gonna start. Hang on. What did I do? What did I do wrong? Mismatch closing lambda. Oh, I didn't close close one of these. That's fine. There's too many of those anyway. Okay, so if we run this, it should spawn 10 threads. That's not 10. That's not 10 at all. That's 8. I have 1, 2, 3, 4, 5, 6. Oh wait, no, I did do print line. Hello? Can I? Alright, and now it goes in the correct order. Now I have 9 of them. Alright, I think it doesn't actually wait for... No, of course, it just like closes everything once it gets here. I bet your ass if we do thread sleep duration from underscore second. If you just wait for 2 seconds here, we're gonna get all of them. Yeah, there we go. It actually ends them this time as well. Okay, we didn't actually do the for handle. We didn't join them. We didn't unwrap all of them to be weighted. That's a better way to handle it for sure. I've never done thread programming in any language ever. Handle join unwrap. For handle in thread, did I type JSON? I typed JSON. I didn't type join. Gion. Gion. I'm pretty sure that's like a French name. Join. That's probably also a French name. Okay, so now it should actually stop, and wait for everything to do. Note that join here means wait for the thread to finish. Yeah, I just discovered that. Thank you very much. Thread starts running in the background as soon as we call spawn, so all of them making progress while we wait on the first one, and the rest of the calls to join return quickly. Yeah, we can bump the example up to 100 thread, which is fine. On my Linux laptop, I can spawn about 90k threads before I hit the crash, but the playground has tight resource limits. Fair enough. Fair enough, though. Each thread uses a lot of memory. In particular, each thread allocates space for a sec, which is 8 MIP by default on Linux. Let's use fancy tricks to allocate the space lazily. Yeah, I mean, 8. Hang on. MIB. Not Man in Black. Megabit. Megabyte? Nani the fuck? A unit of digital information equal to a megabyte. Oh wait, these are the actual 2 squared instead of like a megabyte is just a round human readable number, but the megabyte is the actual one. Yeah. I always confuse the two, honestly. Okay, but it's still a lot if we spawn thousands of threads, so there's a limit on how many threads we can spawn. Here's a demo of passing baseballs back and forth across many threads to show how thread switching overhead affects performance as the number of threads grows. I mean, that makes sense. It's looking more complicated than the other examples. Okay, skip it. Threads are a fine way to run a few jobs in parallel, or if you hundred for various reasons they don't scale well beyond that. A thread pool can be a good approach for CPU intensive work, but when a job spends most of the time blocked on I/O, the pool quickly runs out of worker threads, and there's not enough parallelism to go around. If we want to run thousands of jobs, we need something different. I mean, honestly, I could go with like a 8 thread setup probably for what I want to do. But once again, I want to do it this way because I like complicating stuff for myself or something like that. I know, I find it interesting to do. I could better learn it now before I actually need it, and then I have it when I need it, something like that. Let's try the same thing on async await. For now, we'll just type it out and run it in playgrounds without explaining anything. The async example in this introduction and most of part 1 will use the Tokyo runtime. There are several async runtimes. Okay, yeah. Ah, God, I just need 1 second. How did I make a Tokyo main? There we go. So in main, whoop, it's gonna be hashtag Tokyo mine. Okay, there we go. I just need to know that a little bit. So over here, we're gonna get rid of this. We're gonna get rid of this. This is just gonna be print line. Oh, it's why did I remove it? Like all we basically change is this, but we use Tokyo Uh, oh, I haven't installed Tokyo in here. Oh, I probably didn't. No. Cargo. iCargo. Cargo at Tokyo. So it's gonna be Tokyo. Tokyo time, sleep, duration, from 6:1. And we await for that to happen. Yeah, and then over here, I shouldn't have deleted it. We'll just go full. Full. Actually, I need to make this one async. I think full one dot await. No, just full one, full two, full three. I mean, should we just use effect for this? I mean, I guess we can. He's just calling them synchro, just one after the other. Damn it, missed again. That goddamn mosquito. I will get it before it kills me. Yeah, I need to make my main function async. I am well aware. Oh, oh, oh. All the wrong buttons. Wait. Okay, and then over here, it's gonna be async. Alright, and we don't need thread anymore, so we can remove that. Async FM main, filter resolve, could not find main in Tokyo. Did I do an oopsie there? No, I didn't, right? Tokyo main. Yeah, you should be fine. Save it. Uh, Cargo run. Do you need to recompile or something? But you have Tokyo, right? What are Ergtau complaining about? Hello? I mean, with you having Tokyo, I thought this would be fine, honestly. Why are you? Filter resolve, could not find main in Tokyo. Let's just Tokyo dash dash main? You're not runtime, right? That's just honestly I'm kinda confused. What's going on? Oh, I didn't want to log. Excuse me. I wanted the toml and I want this log out of there. Yeah, you just have Tokyo. You can remove this by now. That's fine. Could not find time in Tokyo. Could not find main in Tokyo. What? I could not find main in Tokyo. Tokyo? Tokyo. Cannot find Tokyo main macro. Dependencies Tokyo versions futures is full. Oh, do I need to add the futures is full? Futures is a full. That's not how you should. I've been already writing too much async, man. Features. Alright, then we check out this one. I just still complaining about Tokyo time. Expected. Oh, I need to. No, I don't. What? Hello? Oh, yeah, no. Of course, like as always, the compiler knows best. Because what we do need is these little curly boys. Save it. go to our main file, try to run it. What? Oh no, I'm still doing it so wrong. Ooh. Okay, over here, you just need to be version equals that. We're doing this. We're going to main. Okay, it's at least trying to compile. Probably because now adding all of the Tokyos. Alright, there we go. Alright, yeah, okay. Alright, so now, yeah, I mean, of course, it does it one after the other, because that makes sense. Making a few calls to full one at a time looks like this. Part 2 of 3 will implement a lot of what Tokyo main is doing. Until then, we can just take it on faith that the thing we put in main when we use Tokyo. Okay. First thing that's different about async is that we declare them with the async keyword and we write .await when we call them. That's fair enough. Making several calls to full at the same time looks like this. Unlike the version with the threads above, you always see the version print the start message in order. You usually see it print at the end message in order too. However, it's possible for the end message to appear out of order because Tokyo timer implementation is complicated. Okay. Yeah, and then once again we just make a little vec that we did before. Let mutable features is a new vec, and then we go for n in 1 through 10 futures dot push. We make a new foo n, which are lazy, so they won't be executed yet. Then we join them all together. I'm just gonna be a little bit lazy here. We're gonna be future. I think we need to implement Tokyo Sync futures. Yeah. Boop. So we use that. We just have a little borrow from Tokyo. We say futures join. Oh, future singular. Hang on. Use Tokyo FS Fut. No, that's file system. Sync. Is it in here? Futures? Right on. Future. Oh, it's just a normal futures. Yeah, of course it is, because we're just using normal futures. Why am I making this so damn complicated? Why would we not use normal? Resolved import futures? Is that not a default one? Future, join all futures, future. I would expect this to be just a no, then it should be an STD, because of course it would be. Right, so we just gonna go futures. There we go. Now we do have futures. Yeah, we're still working. Hang on. Join underscore al with the futures. And we just await that. Alright, so now it should be counting from 1 to 10 and stopping from 1 to 10. Let's see what's going on here. Yeah, and they all run like kind of concurrently. I don't think any of them screwed up like we were warned they could. No. Okay, that's fine. Okay, note that we don't wait each call. Yeah, we just join them all together. We wait for that to be done, and that's happy. After that, we happy. But join all is very different. Join method we use as threads. Previously, joining meant waiting on something, but here it means combining multiple futures together somehow. we get to the details part 1, but for now we can add some more prints to see that join all does take any time and none of our foods start running until we await the join future. Yeah, future, not feature. Unlike the thread example, this works even if we bump it up to 1000 futures. In fact, if we comment out the prints and build in release mode, we can run 1,000,000 futures at once. Damn. Okay, that's a lot. That's a lot you can be running at the same time. I do like that. Important mistakes. When we get some hint about how async works, if we start making mistakes. First, let's try using thread sleep instead of Tokyo time sleep in our async function. Everything is one. Yeah, okay. Yeah, because it doesn't use the feature. We're just stopping everything that's running on this thread until we're done with this. So yeah, that does make a lot of sense. Everything is one at a time again. It's an easy mistake to make. Unfortunately, there have been attempts to automatically detect and handle blocking an async function, but has led to performance problems. It has been possible to handle all cases. As we work through part 1, it will become clear how thread sleep gets in the way of async. For now, we might guess that these full functions running at the same time are actually running all on one thread. Make us try awaiting each future in a loop, the same way we originally joined threads in a loop. Yeah, but that's just gonna go like the same thing. It's gonna be one at a time. What they're saying is the future don't do any in the work any bin bracket text are futures. They'll run in the background. They'll run in the background. We'll get to those in part 2. Instead, they do their work when we dot await them. If we await them one at a time, they do their work one at a time. But if we somehow join all, let's just await all of them at the same time. Yes. All right. Well, I mean that's just a good introduction into different problems here. Part 1, futures. All right, just gonna have like a little overview. Hang on, mosquito. No, it flew away again. God fucking damn it. Yeah, I think it's gonna be it's gonna be a good one for me to actually walk through this, see what's happening, see how this actually works, before I start implementing them. So I'm just gonna make a little bookmark. See here. So this async thing, whatever. It's over there. It's async. We'll figure it out. All right. For now. Hang on, let me pause those ads because they were going to start in a minute and they'll be set because I am sadly implement these nuts. Done. I implemented those nuts. What now? They don't do anything. But that's fine. They're dead code. Never constructed. Never used. That's fine. We can keep it that way. Alright. Yeah, I'm gonna call it there for today because I would like to get started on this with like a fresh mind. So that's gonna happen. Hang on, just one little second. I'm gonna have a look at my calendar because I believe I got Saturday all day to do whatever the heck I want. But I'd like to confirm that. I was absolutely right. Yeah. So I'll probably be doing some more programming on coming Saturday. Um, I, however, will also be back Thursday evening. Probably be a little bit later, starting around like half past eight, 9, instead of my what I'm trying to do at 7. So I hope to see you all there. I hope you all have a wonderful week. Thank you all for being here, for lurking, chatting. I do appreciate it as always. And now I need to find someone to rate y'all lovely people too. Nobody I know seems to be online. Let me check if there's somebody else doing some programming. Or I'm open to suggestions if y'all know anyone. Can I just mark this by English? English tag, please. I want an English tag. Thank you very much. Alright, and what if we add Rust? Boop. There's a few people doing Rust. Finding the longest line of sight in whatever. That's fair enough. I'll hand you over to this lovely person. I do not know them. Tom underscore BH. I hope they're nice. I hope you all have a wonderful week again, and I hope to see you all Thursday.